Over the past few weeks, we've had a chance to talk about derivatives, and we've just focused on finding the first derivative of a variety of functions. Now we're going to take the chance to talk about higher order derivatives. Let's take a look. Let's move from left to right along the graph of f of x equals x cubed plus x squared minus 5x plus 3, and describe how the slope of the tangent line changes as we progress along the curve. So if we take a look at our graph here, we have our graph and the curve is labeled f of x. Just a quick note about when we graph functions, make sure that you have the curve labeled so we know exactly which function we are seeing, especially if we're going to have more than one curve on our graph. Also make sure that you're labeling your axes. This is a little cut off here, but make sure we clearly label that this is the x-axis and this is the y-axis. All right, let's take a look and let's describe the slope of our tangent line as we go throughout the curve. And a variety of points are labeled here for this function, so we'll take a look at those points. So starting at A, we notice that the slope of our tangent is positive and less positive. And we see there's a point here, a maximum, where the slope is going to be 0. And at C, our slope is negative. At D, it continues to be negative. At E, we have a maximum or a minimum, so a slope of 0, and it's going to be a minimum specifically. We're going to have F, where our slope is positive, and everywhere after that, it's positive with an increasing value. And we can see these points are described here on the page as well. At A, at x equals negative 0.3. At B, x equals negative 2, a point just before the local maximum. C, at x equals negative 1, a point just after the maximum and before the local minimum. At D, x equals 0, the y-intercept just before the local minimum. At E, at x equals 1, the local minimum, which is also an x-intercept. And F is at x equals 2, a point just after the local minimum. We can relate what's going on at each of these values to the derivative of our cubic function. We know that our derivative function tells us all about the slope of f of x. And so we can actually find our function, or find the function of our derivative, and we've looked at that and using a variety of rules. So I'm going to rewrite out the function here, and then we'll quickly find the derivative, and then we'll take a look at its graph. So my function was f of x equals x cubed plus x squared minus 5x plus 3. So I find the derivative of each of those pieces, and using the rule of sum and the rule of difference, I can put that together. And so we're going to have f prime x is equal to 3x squared plus 2x to the power of 1. I don't need to write the 1, so just x minus 5, and the plus 3 is gone. So this is my derivative. So no surprise, it is a quadratic function. It's to the power of 2. So let's take a look at our graph here. And we can see this is our y-intercept. We have our y-intercept here of negative 5. Let's make sure our axes are labeled here, x and y. And we don't need to really identify any other characteristics right now. Just we can see that it's been graphed properly. So let's focus on f prime x. What if we wanted to consider the slope of the derivative function f of x? Can we graph this new function on top of f prime x? So in other words, we found the derivative once. I had my parent function up here. That was fine. I found the derivative. Can I find the derivative of the derivative? Can I find a function that describes the slope of the tangents to my derivative line? And yes, of course I can. Because I know I can find the derivative of a function like this. I also know I can find the derivative of a function like that. That's totally fine. So this is why it's called a higher order derivative, because we're going to take the derivative of our derivative. So first of all, we can find that mathematically. So let's do that right away. We know how to do something like this, and we'll see some slightly new notation here as well. I'm going to have 2 apostrophes because it is the second derivative of f of x. So one derivative, second derivative. And we'll just follow our same rules. Multiply the exponent times the coefficient. So 3 times 2 is 6. Subtract 1 from the exponent. So instead of being to the power of 2, it's to the power of 1. And I don't need to write the 1, so that's fine. Plus 2. And of course, we see the shape is going to change once again as well. If our original function was cubic, which it was here, our first derivative is going to be quadratic, 1 degree less. And our second derivative here is going to be a linear line. So let's describe what's going on here with the graph, and then let's try sketching that new linear line. So as we move left to right, I see that my graph is going to have a negative value. Let's identify our x-intercept here, and the graph is going to be negative everywhere we look until we reach our local minimum, where it's going to have a value of 0. After that, as I continue to the right, my graph is going to be positive, and it's going to be increasingly positive everywhere I look, but it's going to be positive everywhere. A couple other things you want to consider. Is this differentiable everywhere? So consider, is it smooth? And is it continuous? And in this case it is, so the derivative exists everywhere. That's no problem. We don't really need to worry about it. And let's try graphing our second derivative. Let's try graphing our f prime x. What do I know about it? Well, I know that at this point here, when x is equal to, looks like about -1, it's going to have a value of 0. So slope at this point is 0. So here, and I know coming from the left here, everything up until this point, the slope of this line everywhere was negative. So all my values are going to be somewhere around here. After this point, the slope is always going to be positive. So after my x-intercept here, every value is going to be positive. And we know it's going to be a linear line, so it's going to be something like this. So let's do that a little neatlier. We already know what the function is. We've already kind of found it mathematically. We've already approximated what the shape is going to look like on the graph. So let's put those two pieces of information together. I know my y-intercept is going to be 2 when x is 0. Y is equal to 2. And we know the slope is 6. So let's sketch that real quick. And we don't have numbers on this graph, but basically we'll see it's going to look something like this. There we go. And let's label. Remember, especially because we have two curves on our graph, we're going to want it to be clearly labeled, and this is our f double prime x. Or this is the second derivative of f of x. And there we go. There's no problem with that. We're doing the exact same things. We're just doing them more than once, which we have not done previously. And the question is now, we know that we can do it, and it kind of makes sense. We know that the degree or order of our function changes each time we find the derivative. So if I start with the cubic function, I go to a quadratic function, I go to a linear function. If I decided to find the third derivative, no surprise, that would just be, we can do that quickly, f triple prime x to the third derivative of f of x equals 6. We would just have some flat line. It's not strictly necessary. I'm not going to leave that on our graph, but we could, and that would be fine. But what's the point? Why do we want to find higher order derivatives? What does the second derivative and so on tell us about a function? Well, let's go ahead and find out. Before we get that far though, let's briefly talk about notation. So to determine how the slope of the tangent is changing, so rather than finding our change in x versus y, we're finding our change in slope versus y, I guess. So to determine how the slope of the tangent is changing, we differentiate the derivative f prime x. If f prime x is differentiable, then the derivative of the derivative function can be found. This is known as the second derivative of f of x and is denoted in function notation as f double prime x. This is read as f double prime of x. In Leibniz notation, the derivative notation is denoted as, so, original first derivative is like dy dx. So we're finding the second derivative, so we have an exponent there of 2 over dx squared. And so we can see that written here as well. We're finding the derivative with respect to x of dy dx. So basically, second derivative of y with respect to x. So that's just your Leibniz notation. So just be familiar with that. Let's take a look at a specific example and see what this looks like once again. Example 1. Find the second derivative of f of x equals x to the power of 4 plus 3x squared minus 5 to the power of x. Remember, the first thing we're going to want to do here is switch from having a square root or a root notation to expressing it in terms of exponents instead. So let's start with that. First step, I'm just going to rewrite my original function. F of x equals x to the power of 4 plus 3x squared minus 5 x to the power of half. Let's find that first derivative using our derivative rules that have come to be our friends over the last few weeks. F prime x is equal to 4x cubed plus 6x minus half times 5 over 2 x to the negative half. All right, that looks fine. Now, we're not going to simplify, so don't try to collect like terms or factor or anything. Just leave it the way it is. Don't simplify. Next up, we're going to find our second derivative. So let's go ahead and do that. Same idea, f double prime x. Let's follow our usual rules. Our first term, 4x cubed, becomes 12x squared plus 6, x goes away. Now I'm going to have negative 5 over 2 times negative half, which is going to give us 5 over 4. So positive 5 over 4, x to the and negative half, minus 1 or minus 2 over 2. It's going to give us negative 3 over 2. All right, that looks pretty good. And now we can rewrite this and see if we can, like basically this is fine. We could leave it this way, but let's tidy it up. Let's switch back to our root notation. So we're going to have 12x squared plus 6 plus 5 over 4 x to the 3 over 2, because we normally want to get rid of our negative exponents and express things with a positive exponent. And if we were asked, we could also represent it like this, 12x squared plus 6 plus 5 over 4 and square root of x cubed. So there we go. We have successfully found our second derivative of this function. And we can do a quick sanity check and just make sure that the degree of our function, or the degree of each part of our function, has decreased if we like. So originally we're dealing with a quartic function to the power of 4. First derivative is cubic to the power of 3. And our second derivative is squared, so quadratic. Looks good. My second chunk, which, like, this is fine. We've kind of already done our sanity check. We can take it one step further, though. Looking at the second term, we've gone from squared to the power of 1 to no exponent, so like to the power of 0. And for our third term, we've gone from the power of half to the power of negative half to the power of negative 3 over 2. So everything looks pretty good here. And if we want, we could graph this quickly in Desmos. I'm not going to take the time to do that in this video, but now would be a great time to pause, to explore this in Desmos, graph all three, or you can even open your derivative machine Desmos graph and play around with this and see if you can add a derivative of the derivative section. So please pause the video and play with that for a moment here if you have the chance to do so. Moving on. Now that we have some idea what we are doing, I would encourage you to pause the video and try this on your own. When you're ready, please go ahead and follow along. Let's find the second derivative given that y equals 5x minus 3 over 2x. So the first thing I'm going to do here is see if I can simplify or rewrite this a little bit. So we can rewrite this as y equals 5x minus 3 times 2x to the negative 1. And we could then multiply through using our distributive property, or we can think of it like this. Y equals 5x over 2x minus 3 over 2x, which is going to give us y equals 5 over 2. The x's cancel out, minus 3 over 2 times x to the negative 1. And now we can just kind of evaluate this using our power rule or our constant multiple rules. So let's go ahead and find our first derivative. I'm going to rewrite this off to the side here, and then we'll go ahead. So y equals 5 over 2 minus 3 over 2 x to the negative 1. Let's find our first derivative, y prime. Actually, I should use the Leibniz notation that they are using in the question here. So let's label first derivative, and we are going to have dy dx equals, so the derivative of a constant is 0, so that's going to go away. We're going to multiply our exponent by our coefficient, so negative 3 over 2 times negative 1 is positive 3 over 2, so 3 over 2. And subtract 1 from our exponent, so x to the power of negative 2. Looks pretty good. Let's find our second derivative. And so we're going to have d squared y over dx squared equals, and same thing once again, exponent times coefficient. So we're going to have negative 6 over 2 x to the negative 3. And obviously we can rewrite this in a little bit tidier form. Negative 6 over 2 is just negative 3 x to the negative 3. And if we want to rewrite this one final time with a positive exponent, we can rewrite this as negative 3 over x to the 3. And that negative in front of the exponent gets used up, bringing it down to our denominator, if you'd like to think about it that way. Once again, I would encourage you to pause the video, jump over to Desmos and check this out. Try graphing each of these lines and see what they look like. And once again, as a quick sanity check, let's just make sure the degree or the order of our function is decreasing by 1 every time. So if my original function was to the power of negative 1, second function, or sorry, first derivative is to the power of negative 2, second derivative is to the power of negative 3, or positive 3 on the bottom there in our denominator. So that looks pretty good. That's our quick sanity check. Once again, please practice graphing and take a look at these to get a feel for whether we're on the right track and what the relationship is between those graphs. In our next example here, hopefully you can pretty quickly, well, once again, I would encourage you to pause the video and try this before watching me answer this, but assuming you've done so already, so consider what kind of function this is and what rules we might need to differentiate this function. You hopefully notice pretty quickly that we have an outside function, something to the power of 7, and another function or expression on the inside of our brackets. And what does it mean when we have a function inside another function? Well, that tells us it's a composite function, and that tells us that we're going to want to use our chain rule. So let's remind ourselves off to the side here, what does chain rule look like? I find that helpful to write out every time we do this, just to keep track of things. So f prime x is going to be equal to g prime u times u prime. And let's identify our functions. So my and u is just equal to h of x, as we've seen before. So first of all, my outer function is going to be my g of x. So my outer function here is going to be, so g of x equals x to the power of 7 And, sorry, not x. I want to use u to represent my inner function, so this is going to be g of u. All right, so g of u is equal to u to the power of 7, which means g prime u is going to be 7 u to the 6th. My inner function u is equal to my inner function h of x, which is going to be 4x cubed plus 3x squared, and u prime h prime x is going to be 12x squared plus 6x. All right, now that I have my pieces together, let's apply chain rule. So the first derivative, f prime x, is going to be g prime of u. So g prime is right here of u. So 7 u to the power of 6. What does u equal? U is just my inner function, and that's what we have identified right here as well. So 4x cubed plus 3x squared times u prime, which is my h prime x, which is that term right there. So times 12x squared plus 6x. All right, that wasn't too bad. I'm just going to tidy up my notation here a little bit to be very clear. We have found the first derivative. And is there anything we can do to clean this up a little bit before we move on? Is there any simplifying we can do? As a matter of fact, there is. So first term 7, can't do anything there. 4x cubed plus 3x squared. There's no like terms. There's nothing I can do there to make that any easier. What I can do here is notice that each of these coefficients is divisible by 6. So I can actually take out a greatest common factor. Let's go ahead and do that. So I'm going to have 7 times 4x cubed plus 3x squared times 6 times 6 times 2x squared plus x. Now, technically, I could factor some x's out of the first and second factor here, like out of each bracket. But I don't think I want to do that. I want to be able to use my constant multiple rule. In order to do that, my first term needs to be a constant. So I can't pull the x's out right now. I could pull the x's out and solve using that method, but I'm not going to do that in this case. So I'm purposely leaving the x's in here, and instead, I'm just going to notice that I can multiply these numbers together, 6 and 7, to get 42. And then 4x cubed plus 3x squared to the power of 6 times 2x squared plus x. So basically, I'm going to be able to use product rule here and constant multiple rule here because there's a constant multiple in front. So f prime x, so first derivative of this function is given here. Let's just label our pieces here. So I'm going to have a constant multiple. And for this piece here, I have two functions being multiplied together, so we're going to be able to use our product rule. And let's remind ourselves quickly off to the side, what does product rule look like? And we recall that if f of x equals g of x times h of x, then f prime x is going to be equal to g prime x times h of x plus g of x times h of x. All right, with that in mind, let's go ahead and attempt to find our first derivative here. And I'm going to label each of my pieces here just to make my life a little easier. So my g of x is going to be the first term, so it's going to be 4x cubed plus 3x squared to the power of 6. And my derivative, I'm going to need to use a chain rule here because it's a function inside another function. So g prime x is going to be equal to 6 4x squared cubed plus 3x squared to the power of 5 times the derivative of the inner function, so times 12x squared plus 6x. So far, so good. And our second term, or h of x, is going to be derivative of this piece right here equals 2x squared plus x, and the derivative of that function, h prime x, is going to be 4x plus 1. So let's put our pieces together using our product rule as a guide. So our constant multiple, I'm actually going to move my label here for a moment so I have a little more room to work. All right, so our constant multiple is just hanging out here at the front. So f double prime x equals 42 is just going to hang out in front. And once again, we're using product rules. So I'm going to have my g prime of x to start. And we saw that my g prime of x is equal to, right here, 6 times 4x cubed plus 3x squared to the power of 5 times 12x squared plus 6x. And as part of our product rule, I need to multiply by my h of x. So let's go ahead and do that. And we can kind of highlight this as we go. So I've done the g prime of x. Now I'm going to do my h of x, which we know is 2x squared plus x plus g of x. So plus my g of x is 4x cubed plus 3x squared to the power of 6 times h prime x, which we found here. So times 4x plus 1. All right, so we're just following our rules. We're just applying them one piece at a time. It is getting a little messy though, but fortunately we will be able to find some common factors and tidy this up a little bit in our next step. All right, so we'll actually notice pretty quickly that we do have some common factors here, and we have a common factor right here, and that is 4x cubed plus 3x squared, and to the power of 6 here, and to the power of 5 here, which means I can pull out 5 of those. Are there any other greatest common factors we can maybe pull something out? Yep, if we look here, I can also pull a 6x out of there. So let's go and do this one piece at a time. So f prime x is equal to 42 times 4x cubed plus 3x squared to the power of 5. That's the most I can pull out. And we'll come back to this part in a moment. I'm just going to have 6 times 12x squared plus 6x times 2x squared plus x. And I pulled out 5 of these. There's 1 left. So plus 4x cubed plus 3x squared times 4x plus 1. Next, let's deal with that greatest common factor we mentioned. So I'm going to pull a 6x out of here. So 42 times 4x cubed plus 3x squared to the power of 5. And we're pulling, like I said, put that in a different color here. We're pulling the 6x out. So we're going to have 6 times 6x, we're going to have 36x. And left and actually, I know some people are going to be confused if I do that all at once. So let's do this one piece at a time. 6 times 6x, and we're left with 2x plus 1. So this part and this part are equivalent. I've just factored that part. I've taken out the greatest common factor. Times 2x squared plus x plus, and I didn't change anything here, 4x cubed plus 3x squared times 4x plus 1. All right, is there anything else I can do to tidy this up? Anything else I can factor or bring together? There's a couple factors I can multiply together, and we can like start to expand now, and then we can collect some like terms. So I'm going to have 42, 4x cubed plus 3x squared to the power of 5. And quick note here, this is when you want to make sure you're writing neatly. so that you don't accidentally like smush this into a 4 or something. So especially when there's a lot of steps on the page, make sure you're writing neatly. I've seen students make easy mistakes simply by misreading their own numbers later on. All right, what else can we do here? We can multiply our factors. So I'm going to have 6 times 6x is going to give me 36. Oh, and I'm going to go back to the previous step, just so I don't run out of room here. I'm also going to factor an x out of here. So I'm going to rewrite that for a moment. So we're going to represent this as x times 2x plus 1. So right now, in this line, I'm multiplying the 6 by the 6x by the x. So I'm going to have 6 times 6 is 36, x times x is x squared. I'm going to have 36x squared multiplied by what's left? Well, we're going to have 2x plus 1 times 2x plus 1. So that's going to give us 4x squared plus 4x plus 1 plus, stick with the red, plus, and we're just going to multiply through double distributive property. I'm not going to show all my steps here, but we're going to end up with 16x to the power of 4 plus 12x to the power of 3 plus 4x to the power of 3 plus 3x squared. So once again, we're just using rules we're familiar with. Nothing here is new. It's just a little scary because there's a lot of terms to keep track of. We're doing all right, though. Let's keep going. Next line. Is there anything else I can common factor out? Yes, I can actually factor out some x's here. So I'm going to factor out an x squared from each of these. So we're going to end up with 42x squared times 4x plus 3 to the power of 5. Inside the brackets, can multiply through again. So we're going to have 100, and I'm multiplying these two together right now. 160 x cubed plus 160, so x to the power 4 x cubed plus 30 . I'm going to double check this for a moment. Sorry, let's take a step back here. I'm skipping a step if I go straight to those numbers. So 36 times 4 is 144. So 144x to the power of 4, and 36 times 4 is 144 x cubed plus 36x squared, and then plus these terms as well. So plus 16x to the power of 4 plus 12 and 4x cubed is going to be 16x cubed plus 3x squared. Almost there. Let's collect some like terms now. So we're going to have to the power of 4 these terms, to the power of 3 these terms, to the power of 2 these terms. So let's bring that all together. So 42 x squared 4x plus 3 to the power of 5, and 144 plus 16 gives us 160 x to the power of 4 plus 144 plus 16 is 160 x cubed, and 36 plus 3 gives us 39 x squared. Almost done. Are there any additional greatest common factors we can pull out? Well, yes. I can pull out some of my x's here. So let's try this once again. So we're going to have 42x squared, 4x plus 3 to the power of 5. We're going to pull out x squared. And we're going to be left with 160x squared plus 160x plus 39. All right, and I just realized I made a slight mistake. I'm going to finish this up, though, and then I'll go back and we'll correct the mistake together. It's not too bad. We're not going to have to rewrite too many things, just a little bit. And I'm not going to redo this whole question because it takes a lot of steps. The point is to get an overview of how to do this. So sorry for the mistake, but we'll fix it up in a moment. So let's finish. This won't be the right answer, but we can fix it afterward. So we're going to have 42x to the power of 4 times 4x plus 3 to the power of 5 times 160x squared plus 160x plus 39. All right, the mistake I made, and this won't be too bad to fix, is that when I went from this step to this step, I factored out the x squared, but I can't just yank that out. I have to remember that it's to the power of 5. I got distracted looking at all the numbers here, and so we're going to fix that. So what I had here was I'm going to redo it off to the side here. I had 4x cubed plus 3x squared to the power of 5. If I want to take that x squared out like I did, I can write it as x squared times 4x plus 3. That whole thing is to the power of 5. So basically, if I'm trying to take this out, this is the same as x squared to the power of 5 times 4x plus 3 to the power of 5. So this part can stay the same, that's fine, but I forgot to do my exponent rule here where I'm finding the exponent of an exponent. So this is equal to x to the power of 10 times 4x plus 3 to the power of 5. So when I pulled it out in this step here, I should have really done it to the power of 10. So let's fix that. Power of 10. And 10 and 10, and then now when I'm multiplying these two together, using my exponent rules, multiplying two numbers with the same base, I add the exponents. It's going to be to the power of 12. So there we go. That wasn't very fun, but we have successfully found the second derivative. Once again, I would encourage you to stop the video here, go ahead and play around with this with Desmos, try graphing all the functions, seeing the relationship between them. And we didn't do anything new here. We just used our chain rule and our product rule. It just isn't very nice because there's so many terms and it ends up getting a little messy. Easy to make small mistakes along the way like I did. But generally we can see that we can apply our rules and find derivatives and second derivatives even when things get a little unnice. I'm going to stop the video here, but in our next video, now that we've practiced finding the second derivative, we're going to discuss what does the second derivative tell us graphically about our original function. And this is where we're going to be learning a little bit more about curve sketching and using the second derivative to inform the shape of our graph when we're trying to make an accurate graph of our original function without using technological tools like Desmos.